Good morning. We are entering into the last day of the first trimester of this school, and the first lecture will be by Zohar Komargodski, who will talk on dynamics in 4-dimension and domain walls. Zohar.
Okay, thanks. I'll just quickly first review the previous lecture, and then we'll proceed. So I'll just remind you quickly what we've done in the previous lecture, since it was already 2 days ago. So in the previous lecture, we discussed the concept of symmetries, ordinary symmetries and higher symmetries. We discussed how the group structure emerges from the axiomatic definition of symmetries. And we also discussed the concept of higher groups, which is a non-trivial combination of ordinary symmetries with higher symmetries. Then we defined the concept of anomalies. So anomalies arise when the free energy is not gauge invariant. The free energy of the system is not gauge invariant. The free energy as a function of various sources is not gauge invariant. And anomalies arise when the non-gauge invariance of the free energy is associated to the singular parts of the free energy rather than the analytic parts of the free energy. And when this is true, it follows that there must be a non-trivial infrared limit to the Hamiltonian. So the Hamiltonian cannot be completely trivial at long distances. For instance, the wave function cannot be a trivial product state. So that's the general definition of anomalies. And then before we jump into Yang-Mills theory, which has all sorts of subtle issues connecting these concepts, I wanted to cover a toy example which has some ingredients which are useful to know in order to understand the Yang-Mills case. So the toy example consists of a particle moving on a ring with some potential and some theta parameter, which is classically inconsequential, but quantum mechanically this theta parameter makes a difference. So the theta parameter quantum mechanically can be thought of as a magnetic solenoid that pierces the ring with some flux that's equal to theta. And the 2 pi periodicity of this theta angle is just the familiar fact from the Aharonov-Bohm effect that when you have a solenoid with integer flux, then it makes no difference, neither in the classical nor in the quantum theory. So, and then are there any questions about it? Any leftover questions from either the tutorial session or the lecture? Yeah, in the tutorial we covered the concept of higher groups in a little bit more detail. So those who were there could have benefited from that. Okay, so then we studied the toy model just to warm up with no potential on the ring whatsoever, in which case you can quantize this Hamiltonian straightforwardly, and you get this kind of spectrum. As a function of the theta, this is the theta parameter. As a function of the theta parameter, you get the states, which are labeled by an integer with this wave function, and these are the energies of those states. And it's manifest that the spectrum of the theory is 2 pi periodic. And the curious thing is that when you set theta equals pi, you have a twofold degenerate ground state, which is spanned by these two states. So you have a qubit. Okay. So there is a qubit at theta equals pi. And what I wanted to show you is that while you may be familiar with the Witten index technique that allows to compute the degeneracy of the Hamiltonian or supersymmetric quantum mechanics, what I want to show you is a technique to study interacting quantum systems without supersymmetry, and you would still be able to prove that those two states have to be degenerate under some circumstances in the full interacting theory where we add some potential to the theory. So that's the main purpose, to teach you this technique, and then apply some of those ideas to more interesting higher dimensional quantum field theories. Okay, so I'll start. So we discussed the fact that at theta equals 0 and pi, these 2 points are distinguished by the fact that the symmetry group at those points is a little bit bigger than the symmetry group at generic theta. So while at generic theta, the symmetry group is of this model with no potential is SO2, corresponding to just translations on the ring. At theta equals 0 and pi, the symmetry group of this model is in fact O2. And the classical group relations of O2 are familiar. If you perform a reflection, rotation, reflection, you get a rotation by the opposite of the angle. So this is the classical O2 group. And alpha is just a rotation by some angle, and therefore alpha is a 2-pi periodic parameter. So now the question is, what happens to those classical group relations that define O2 when we try to implement them on the Hilbert space of the theory? And you'll see that that's where the juice is in. All the juice is in the fact that something weird happens to that group relation when you try to implement it on the Hilbert space. So let's start from theta equals 0 and do some little computations. At theta equals 0, we have all these states. And since the energy, let me also write the energy just for reference. The energy of the state is a half n minus theta over 2 pi squared. So the energy of the nth, energy of the nth state, the n excited state of the particle on the ring is given by this formula. And so you may observe that the theta equals 0, the state n and the state minus n are degenerate, and the only ground state is n equals to 0. So we have to try to realize those. We have to try to realize the O2 symmetry on that Hilbert space, and that's kind of straightforward. We promote the rotations by an angle alpha on the ring to an operator in the Hilbert space, and we just define the transformation property of the nth state to be e to the I alpha n times n. And that's obvious since this is the wave function. So that's what happens if you translate q by an angle alpha. And now you have to define how reflections act on n. This can only be defined at theta equals 0, because only at theta equals 0 and pi there is reflection symmetry. It's actually somewhat non-obvious, but if you put a half integer magnetic flux here, the system is still reflection invariant. But for generic magnetic flux, it's not. So it's only 0 and pi where there is reflection symmetry. So reflection symmetry acting on n, you have to guess the answer. So since the group classically obeys that reflection square root to 1, and then reflection rotations reflection obey this property, you have to have something that would square to 1, and you still need it to act like q going to minus q. So of course this gotta be the answer, and there is no other inequivalent answer you could try to write. You could put some phase here, but then you have to make sure that this is true, and you can remove that phase eventually. You can argue that that phase can be removed, and now you do a small computation. You check whether this action on the Hilbert space of the qubit, of the free qubit, this action on the Hilbert space of theta equals 0, the theta equals 0 model, you can check that this obeys this group relation. So as operators, this relation is obeyed on the full Hilbert space. So there is no problem realizing the O2 symmetry, which is a classical symmetry, on the Hilbert space of the particle moving on a ring without a solenoid. But now let's try to see what happens if we try to realize the O2 symmetry that's at theta equals pi, where there is a half integer solenoid. And that's where things become much more interesting and mathematically non-trivial. So now let's study the Hilbert space at theta equals pi. Are there any questions about this at theta equals 0? Okay, so at theta equals pi, it's still true that this has to hold, since this is kind of obvious from the structure of the wave functions. It's still true that rotating by alpha the state n, you gotta get that. But trying to understand what the reflection does is a little bit less obvious. Notice that at theta equals 0, n and minus n were energy degenerate, and therefore this formula made sense. But at theta equals pi, this formula makes no sense, because n and minus n don't even have the same energy. For instance, at theta equals pi, 0 and 1 have the same energy. So on the other hand, so while n and minus n don't have the same energy, n and minus n plus 1 do have the same energy. And therefore, you are compelled to try to connect n to n plus 1. To minus n plus 1. So you're compelled to write a formula like that. There is no other formula you could try to write.
Can't you also just say that n is the canonical momenta, and so if you express it in terms of q dot, then you just use q goes to minus q?
N is the canonical momenta.
That's right, and so that's related to, that's q dot plus theta
Yes, yes. So this is your.
This follows from Q goes to minus.
That's right. This is the only consistent thing with the structure of the energy spectrum, for instance. Now, you can also try to put here some phase. Okay, you can try to put here some phase. And an interesting exercise that you have to try to do at home, it's a really educational exercise, is to repeat whatever I'm going to say here without putting any phase, and you'll see that the conclusions remain unchanged. You can show that any phase here can be removed by some transformations of variables, redefinitions of states, and so on and so forth. So I'm going to proceed the discussion without putting any phase here. And you'll try to prove at home that that's inconsequential, that this phase is not very important. So what are the interesting properties of this transformation? So first of all, cis head squared obeys the classical group relation. So we haven't violated the fact that reflection square to 1, because if you apply this twice, perhaps you can see it quickly in your head, you land on your feet. Because if you apply a minus sign here, you get n minus 1, you add another 1, and you get back to n. So we haven't messed with that. In addition, we haven't destroyed the fact that v2 pi is 1. So a rotation by an angle of 360 degrees is still a trivial transformation, as you would expect from the classical group relations. However, if you compute this, you get something interesting. You can try to compute it. It's straightforward. You can compute it on the state n. And what you find is that the classical group relation is not obeyed. So you can try to take the state n, acting by c, you get minus n plus 1. Then you rotate, you get e to the I alpha minus n plus 1. You act with c again, and you get the state n again, but with some phase, which is e to the minus. You get a phase which is e to the minus I alpha n minus 1. And that's not quite the same as acting with v minus alpha. There is a mismatch. But amazingly, this mismatch is independent of n. And this is why there will be some interesting discussion to be had. So what we find, I just want to be careful about the sign here. Yeah, I think it's probably a plus. Yeah, so what we get is e to the I alpha v minus alpha hat. And this is very confusing, that you don't seem to be able to maintain the classical symmetry, the classical O2 symmetry of this model. Let me remove that. And there is a pesky phase that creeps in. Okay, so there is a pesky phase that creeps in, and we have to try to understand what it means. So the first observation about this phase, which is very important, is that it's independent of the state on the Hilbert space. It's proportional to the unit matrix, to a scalar matrix on the Hilbert space. So it's by itself, this phase is what we would call a C number in quantum mechanics, because it doesn't act on the Hilbert space. So this phase is a C number. That's a very important fact. So our violation of the classical groups, of the classical group relation, was not too violent. It's just a C number. The second thing is that you can try to remove this phase. You can ask, okay, is this phase really important? You might, if you've ever read like the original paper of Majorana, he also encountered some funny phase, and he actually removed it by redefining things by i's. So you can ask, okay, let's redefine, I don't know, like c by I. Would that go away? Well, you could redefine c by I, and it would seem to go away, at least for alpha equals pi. But then you would destroy this, for instance. So you can try to remove this phase, but what you find is that it's irremovable. So you can remove almost everything, but not quite everything. So the best thing you can try to do is to try to redefine the operators in the following manner to try to remove this phase. You can try to redefine the operators in this manner, e to the minus I alpha over 2. And then the classical group relation would seem to be obeyed again. Sorry, plus alpha, and this would be minus alpha. So the classical group relation would now be obeyed if you were to do this redefinition. But you've messed with something. The periodic, exactly. Now 360 degrees rotations are not a trivial operation on the Hilbert space. In fact, they are not a C number even. You see that, well, what I want to say is that for alpha equals 2 pi, this is non-trivial. it's a C number on the Hilbert space, but it's not an identity. So you still could not save the classical group relation. But this makes it a little bit easier to understand what we're dealing with. This is like trying to say, this is trying to tell us that the symmetry that acts on the Hilbert space is some sort of double cover of the symmetry of the classical model. So the symmetry that acts on the Hilbert space, is not O2, but it's a certain double cover of O2. Does anybody know how double covers of O2 are called? Like as a student. Exactly. So this is called the pin2. And this is an example of a central extension. You might be familiar with the central charge from the Virasoro algebra. The central charge is also a unit matrix, and it's exactly the same thing. This is the quantum mechanical analog of what a central charge is. So we can think about it as a discrete central charge. If you were to study the representation of the operators on the projective Hilbert space, you would get O2, so you would land on your feet. But on the full Hilbert space, there is a non-trivial central extension. Now, this has far-reaching consequences for the interacting model that I'm going to explain now. So I would like to explain now the consequences for an interacting model. So now we'll study the consequences of the central extensions. So one thing that is not obvious before I discuss the consequences, I want to argue that this phenomenon is the same as an anomaly. It's the simplest example of a discrete anomaly. And it happens in a bosonic system in quantum mechanics. Purely bosonic system in quantum mechanics, you don't need chiral fermions or none of that. So before we discuss the consequences, I'll just argue that this is the same as an anomaly. So the argument is very simple. Consider the partition function of the model. I want to show you that this is the same as what we defined in the first lecture as an anomaly. This is a phenomenon of a central extension that cannot be removed by a change of variables. So consider the partition function of the model. And this is going to be a partition function as a function of a chemical potential. What is this chemical potential? This chemical potential is going to be a chemical potential for SO2 for the rotation symmetry of the ring. Now, what it means is that we're just counting the states of the quantum mechanical system at some. We put the quantum mechanical system on the circle, which is like temperature, and then we just count the states of the Hilbert space, weighted by their SO2 charges. And the SO2 charges, as you remember, were given by this formula. So let's just compute the contribution to the partition function of the ground state to keep it simple. So at theta equals 0, we have only one ground state, and it was the 0 state. And that state was invariant under SO2. So the partition function is just one. It's mu independent if you don't keep the highest excited state, the higher excited states. But at theta equals pi, there are two states. There are two ground states in the non-interacting model. We have a qubit, and we have to just add them up with appropriate weights that reflect their SO2 charges. And as you remember, that qubit was 0 and 1. That were the two degenerate states at theta equals pi. So this has 0 SO2 charges, while this has charge 1 under SO2. So we would get 1 plus e to the I beta mu. That is the contribution of the ground state to the partition function. Now, this O2 symmetry, the disconnected part of the O2 symmetry, namely the reflection symmetry C, it acts by taking mu to minus mu. Because that's the classical group relation, that if you do a reflection, the SO2 charges are reversed. And you see that this is not invariant. So when we couple the system to background gauge fields, the partition function was no longer invariant under charge conjugation symmetry. And you can try to fix it by adding analytic pieces to the partition function, and you cannot. Just for the more advanced students, let me try to explain why you cannot fix it by adding an analytic piece to the partition function. This is a comment just for the little bit more advanced students. For the others, this should be sufficient, that you see that this partition function is not invariant under charge conjugation. So this phenomenon of central extension is essentially mathematically identical to a 't Hooft anomaly, to an anomaly. So for the slightly more advanced students, you could try to add to the partition function a half of A naught, where A naught is the gauge field for SO2 symmetry. And then the partition function would become e to the I beta mu over 2 plus e to the minus I beta mu over 2, which is charge conjugation invariant. And you could have saved charge conjugation symmetry in this way. But this is not a truly local piece. This is a half-integral Chern-Simons term, which is not properly defined. It's not invariant under large gauge transformations. So you could add something non-analytic and save the charge conjugation symmetry, but this is not an allowed counter term. So that really shows that this non-invariance of the partition function is associated to a non-analytic piece in the partition function. And that's why the ground state of the model is non-trivial. We have a qubit.
Sorry, why is it I beta? Why is it I beta?
You're asking about the I particularly? Why is there an I? It's the I here is just the way chemical potentials appear in partition functions. So you add every state with e to the I mu times the charge of the state. I'm adding an ordinary real chemical potential. Any other questions about it? Okay. Well, here I've added, I took the background gauge field A0 to be real. I took it to be real, like physical real parameter, and I'm going to Euclidean space, and then I get an I. It's the same I that appears in Chern-Simons terms in quantum mechanics. It's a question of terminology, but if you take a real background for A0, you get I. Okay, so now let's get to something more interesting.
Can I maybe clarify? So it's true. I agree that this structure leads to this anomaly, but it's not true that every Atos anomaly comes from this kind of structure on the physical Hilbert space.
I didn't make yet general claims. I'll make soon more general claims.
They're not equivalent phenomena.
I'll make soon more general claims. Any other questions about the free model? This finishes the discussion of, yeah?
So isn't this closer in spirit to the ABJ anomaly, because we are sort of, there's a symmetry which is not there at the quantum level, and it's...
No. The O2 symmetry here is present in the full theory. If you look at the projective Hilbert space, it transforms linearly under O2, and correlation functions in this model are invariant under O2. The ABJ anomaly is a misidentification of the symmetries. There is no action on the Hilbert space of any conserved charge. Here there is a conserved charge. The issue here is much more subtle than an ABJ anomaly. ABJ is just like you got the symmetries wrong, so you're confused. But here there is a physical phenomenon that there is an actual symmetry that acts on the projective Hilbert space and leads to word identities. However, there is a central charge, which is which was somewhere here. This phase, the C number phase that appears in the algebra or in the commutation relations. This is a much more subtle phenomenon than an ABJ anomaly. It's a physical phenomenon. Rather, ABJ is not a physical thing. ABJ is just a misidentification of the variables or the symmetries. But this is a physical phenomenon that leads to a degenerate ground state, which is a qubit. It's something that you can measure. Okay, so, yeah? You're asking about the qubit? The qubit exists only at theta equals pi. Yeah. Exactly. There is a 't Hooft anomaly for O2. However, it's hard to mathematically explain how to couple the system to O2 background fields. I could explain that, but it would take me like an hour. So instead, I've done a trick. Instead of showing you that the full partition function as a function of O2 background fields is not gauge invariant, I've done a slight detour or a slight simplification, which is that I couple the system to background fields for SO2, which by itself has no anomaly. And then I've shown that the action of the disconnected part of O2 on that is non-trivial. And you can, with a little bit more work, show that that leads to an actual ordinary anomaly if you were to be able to couple the whole system to O2 background fields. which is mathematically kind of a little bit more advanced. So I've done some kind of so if you want to think about it as an 't Hooft anomaly, it's like a mixed anomaly. You can think about O2 as a semi-direct product between, let's say, Z2 and SO2. It's a semi-direct product where the Z2 acts non-trivially on SO2. And the anomaly here is a mixed anomaly between those two things. So if you were to couple the system to SO2 background fields, there would be no issue. The partition function is completely gauge invariant. Similarly, if you were to just couple the system to Z2 background fields, there would be no problem. It's only when you try to do both that you find an issue.
This phenomenon to the non-smoothness of the ground state that you get is like that.
This central extension is closely related to the fact that there is a qubit. I'll show you soon why. We'll add some interactions now, and you'll see it in full glory, that there is a close relation. So let's add interactions. As I told you, the motivation of this study is this problem in quantum mechanics that has two ground states semi-classically, but non-perturbatively because of instantons there is one ground state. So we're going to do a similar exercise now, but on a ring with a half-integer flux. So now we have a half-integer magnetic flux through a ring, and we add some potential, which is going to be cosine 2q. And it doesn't have to be just cosine of 2q. It could be a much more general potential. We'll discuss it in a second. But imagine that you add a potential on a ring that's like cosine 2q. Then there are two ground states. And semi-classically, there are two ground states, and classically there are two ground states. But here I claim that all the instantons exactly cancel, and the qubit remains for any value of the coupling of this potential. So this would be extremely hard to show with instanton calculus or ordinary techniques in quantum mechanics. But using topology, you can, using this kind of arguments, which is some sort of discrete topology, as you'll see, you can prove it, which we're going to do now. So the claim is that for this choice of the potential, these two states remain exactly degenerate in the full theory. And as a small exercise, you can try to do the one instanton computation that you are taught in grad school and try to see that the one instanton amplitude cancels out. So it's not always true that quantum mechanics leads to, in the presence of interactions, to lifts all the degeneracies. This is a very cute counterexample. So how does it work? The basic idea is that the central extension does not need the full SO2 symmetry. You don't need the ring to be completely homogeneous to have a non-trivial central extension in the algebra of the charges. Okay, that's the central idea. The point is that even if you just had rotations by 180 degrees and reflections, there would still be a non-trivial central extension. That's the whole point. So let's show that this is true. So suppose your system had only rotations by 180 degrees and reflections. Then this would be a perfectly good potential to write, consistent with those two symmetries, and that's why there is a factor of 2 here, because then it's invariant under 180 degrees rotations. Of course, there is no hope that this would lead to a qubit, this kind of inhomogeneity on the ring, because even classically there is just one ground state. So you can't hope that there will be a twofold degenerate ground state quantum mechanically. But with 2q, you have some hope. And indeed, you can show it mathematically. Because this preserves these two symmetries. Indeed, this is invariant under q going to minus q and under q going to q plus pi. So the algebra, I'm just going to specialize the algebra that we wrote for the free model for those two generators. So what you find is this is the crucial thing, the minus v pi. And c squared, these are all operators on the Hilbert space. And this is, and v2 pi is, v2 pi is 1, and v pi squared is 1. Okay, so that's what you find if you simply specialize the previous results for these two generators. And this minus sign is the hero of this story, this central minus sign. So let me explain mathematically what it means. This minus sign must be a discrete object. It cannot change continuously as a function of the couplings. So the minus sign is a discrete object. it cannot change continuously as a function of the coupling lambda. And that's enough to prove that the twofold degeneracy cannot be lifted. It cannot change continuously with lambda. Okay, and for that reason, it must be true that the ground state is twofold degenerate. Let's prove it. Let's suppose by contradiction that the ground state was trivial, non-degenerate. So there will be some one state, psi. That would have been the ground state. But you cannot realize this algebra with the minus sign on one state. Because whatever C does, as long as C squared is 1, all these phases are going to commute. If you have just one dimensional Hilbert space, the most you can get is a phase. And phases commute.
Yeah, so this is also what I was trying to get at before, because in higher dimensions...
We'll discuss, I'll get to higher dimensions.
Ground state, but nonetheless you have an
I'll discuss higher dimensions soon. In quantum mechanics, this is how it works. So if you just had a single non-degenerate ground state, you would have never been able to realize this algebra of symmetries. And therefore, there must this leads to a contradiction, an immediate contradiction. Another fun fact is that you can understand what does this minus sign mean in group theory language. So what we're talking about is the following algebra. Eta is a phase, C squared is 1, and also V pi squared is 1. We're talking about the following group. And furthermore, eta is central, because it's like the unit matrix. So eta commutes with everything. Now at eta equals 0, eta is plus 1. And then you get O2. But at eta equals pi, eta is minus 1. And you get this group. And this group has a name. This is D8. These are the symmetries of a square. This is the dihedral group with 8 elements, which are just the symmetries of a square. So our Z2 times Z2 symmetry, so this is isomorphic to Z2 times Z2. This is just Z2 times Z2 if you were to ignore the central extension. On the projective Hilbert space, you just get Z2 times Z2. This is Z2 times Z2. These are the symmetries of a rectangle, so to say. But then in the full quantum theory, the symmetry that acts on the Hilbert space is the dihedral group of 8 elements rather than Z2 times Z2, which only has 4 elements. So this central extension is a discrete operation mathematically. There is no continuous parameter in that operation. It's just an extension of Z2 times Z2 to D8. And that's why it cannot depend on the coupling constants, and you cannot have a trivial ground state. And the challenge for you is to try to understand from instanton calculus, how can it be that these two degenerate ground states are not lifted by an instanton? Okay? Now, one fun fact that connects this story to some work from the 80s by, I think, Adam, Eliezer, Shmuel, right? And Frischmann, is the following fact. Are there any questions about this example before I make a comment connecting it to something that was discussed in the past regarding the parity anomaly?
Isn't it the same as Kramer's degeneracy theorem? I mean,
The what degeneracy?
Kramer's theorem.
No, Kramer's theorem is about systems where there is an anti-unitary operator T that scores to minus 1. So Kramer's has shown that if you have a system with an anti-unitary that scores to minus 1, the Hilbert space cannot be trivial and degenerate. Trivial and non-degenerate. Cannot be non-degenerate. The quantum mechanical ground state cannot be non-degenerate. This is similar, but it does not involve space-time symmetries. This only involves internal symmetries. A separate discussion could be had about how time reversal symmetry acts in the presence of a half-integer solenoid. And this was recently discussed in some papers. And there is no Kramer's pair in this problem. So this problem does not have a Kramer's pair. Okay. One physical comment that I want to make, connecting it to some work from the 80s, and also connecting this story to boson-fermion duality. This story is also the simplest example of boson-fermion duality in the following sense. Let's take lambda to infinity. So obviously what remains of the system with this huge potential are just the ground states, and the fluctuations are going to be decoupled. So then the Hilbert space consists of just the ground states, the 0 and 1 states. Which other system do you know with 2 states? Free fermion, right? So at lambda equals infinity, there is a boson-fermion duality, which is extremely similar to how boson-fermion duality works in 2+1 dimensions, where you take a bosonic theory, you take the coupling to infinity, and you get a free fermion. So at lambda equals infinity, this system is exactly equivalent to a single complex fermion. And in fact, in the paper from the 80s that I mentioned, people have studied how the symmetries of a complex fermion act on the Hilbert space, and they've discussed this partition function. They've seen that there is some sort of an anomaly, which is closely related to a parity anomaly. So this is also a very interesting duality, that we get a particle on a ring is equivalent in this limit of large potential to a free fermion. And that also perhaps intuitively explains why a pin group appears. A pin group is a characteristic of a fermionic system. So really this boson that's going around the half-integer solenoid becomes a free fermion in some decoupling limit of that sort. So this is an interesting question that's not solved is how to generalize it to a non-abelian boson-fermion duality in quantum mechanics. That's not known yet. Yeah. Oh, so yeah, you see that this potential is not the only one, in fact. All you need is to preserve, as you understand, Z2 times Z2. So I could have written also plus beta cosine of 4q, whatever, and it would still be true. The only thing that you need is to make sure that Z2 times Z2 is preserved. This system has many parameters, and it would still be true, which is very hard to see with instanton calculus. But it's so those of you who have ever looked at quantum mechanics and the Witten index may find this parallel striking, because it's like a Witten index. The two states cannot pair up, but there is no supersymmetry here. Okay. Now another comment that connects it to more recent literature in condensed matter physics is the classification, the issue of classification of such things. So here we're talking about a central extension. I'm basically getting to Daniel's question. Here we're talking about a central extension of some group G, which could be discrete. And this is also a comment for the slightly more advanced students. Central extensions of groups are classified by H2, G, U1, which is a group cohomology object. If you look at the condensed matter literature, this is also exactly what classifies SPT phases in one spatial dimension, bosonic SPT phases in one spatial dimension. And that's not a coincidence, because SPT phases are the same as anomalies. And the fact that we've utilized here is that Z2 times Z2 has a central extension. And it has a unique non-trivial central extension, which leads to the group D8. So this Z2 just says that there is one central extension that's non-trivial that leads to the group D8, the dihedral group of 8 elements. And that also philosophically sort of explains why in graduate school this phenomenon was not seen. This potential has only a Z2 symmetry, not Z2 times Z2. And it turns out that Z2 doesn't have any central extensions. Z2 has no central extensions. That's why if you have a potential with Z2 symmetry, there's no real mechanism to prohibit instanton proliferation and splitting of the ground state. But if you have Z2 times Z2 symmetry, there is a very natural way to do that, utilizing the central extension. And there is a possibility for an anomaly. So Z2 symmetry cannot have anomalies, but Z2 times Z2 can have anomalies. And that's all there is to it. So in some sense, the rule, or like the majority of problems, will probably be in this class, not in this class.
Can't you also argue that in any system where the Euclidean action is real, you can never have this cancellation between the instances?
Yeah, there is a class of problems where there will be no cancellations, and
That's how usually we study the ones where it's real, where the start out.
Yeah, this is also, of course, a very familiar setup. These are the facts. With Z2, you cannot have any. With Z2, it's really easy that there are no central extensions because, this is Z2, right? So you could have, maybe there is a central element here, eta, but eta squared has to be 1. And therefore, eta is either plus or minus 1. And in both cases, you can remove that by redefining C, and that's it. So there is no way not to non-trivially extend Z2. But Z2 times Z2 can be centrally extended, and there is an anomaly that you can write using discrete gauge fields. And that's the source of this issue. Okay, so this finishes the quantum mechanics, and now I want to get to Yang-Mills theory, QED and Yang-Mills theory, and show you that there are similar new discrete anomalies in those cases. which lead to non-perturbative results about the ground states. Oh, I also wanted to make another comment regarding Daniel's question of whether this is how anomalies work in general. So in quantum mechanics, anomalies are the same as central extensions. In higher dimensions, this is not so. This is more complicated. But in quantum mechanics, it so happens that this thing has an interpretation as a central extension, which it does not in higher dimensions. That's a technical point that I would not try to explain pedagogically. Are there any more questions about quantum mechanics before? Yeah. Can you just speak up? I can barely hear. What's the connection between instantons and lifting the degeneracy? Yeah. If you have a non-trivial central extension, you cannot have a degenerate ground state because some central element is like -1. And it's going to appear in some modification of your classical group relations. And if you had just one ground state, you could never realize such an algebra. Because suppose, okay, so let me repeat the argument. Suppose you had one ground state. So what could C do to that ground state? C squared has to be 1, so it can at most multiply that ground state by -1. And similarly, V pi has to at most multiply it by -1. And so you might get something like -1, -1, -1, but that's also -1. So you'll never be able to realize an algebra like that for eta is -1, like at eta equals pi. It's just impossible to realize such an algebra with a single ground state. Is that more clear? So whenever there is a non-trivial central extension lurking, it's easy to prove that the ground state has to be degenerate. Okay? Any other questions? Yes?
Are you familiar with an example in quantum mechanics where the degeneracy of the ground state is infinite?
Yes? But what's the question?
Can you tell me about it?
It will be like too far afield to discuss it here. Yeah, I can give you the nickname and buzzword, and you can look it up. It's called BFSS matrix model. BFSS matrix model. Okay. Any other questions? Okay. Okay, now I want to discuss higher dimensional systems. So we're switching gears to QED. And then we're going to discuss some QED problems, which are kind of trivial. And then Yang-Mills theory, which is much more confusing and has non-trivial new elements. So we're going to discuss QED in 4 dimensions, 3 + 1 dimensions. Or even just free Maxwell to start. This is mostly just to set up the notations with this Lagrangian, okay? So I want to set up the notations and get back to our discussion of higher symmetries, 1-form symmetries, 0-form symmetries. So you might remember that we've discussed the possibility of having some zero-form symmetries, which are occurrence with just one index. These are ordinary symmetries that act on particles. So QED doesn't have any such continuous symmetries. There are no interesting continuous symmetries with one index. There are like charge conjugation, time reversal, these kind of things. So we're not going to discuss the zero-form symmetries of QED. But Maxwell theory. But it has Maxwell theory has interesting one-form symmetries, which are currents with two indices that are conserved. So there are 2 such currents. One is called the electric, and one is called the magnetic. And they both have 2 indices. This is just F mu over 2 pi. And this is epsilon mu nu rho sigma with another 2 pi. So free Maxwell theory has 2 one-form symmetries, and they commute. You can just check that they commute. So you get the U1 times U1 one-form symmetry. Now I want to explain what the symmetries act on, and then we'll try to guess the answer for non-abelian, for the non-abelian case. Yeah. A what? Yeah, as you remember, a one-form symmetry. A one-form symmetry is a current. In the continuous case, a one-form symmetry is a current with two indices that's anti-symmetric in those two indices, and it's conserved. So it is a two-form.
She's asking why are you calling it one form then? If the current is
You remember that our terminology was the p-form symmetries. That's something that I explained in detail in the first lecture. P-form symmetries, by definition, like semantic definition, they are the same as p plus 1 form currents that obey this equation.
Yeah, the object that's charged.
The charge is going to be something that we'll discuss soon. This is just the terminology. This is the terminology. Yeah, I probably need a 4 pi for the second. Yeah. Maybe I'll just put like star, and then I don't need a 4 pi. Okay.
Then for you,
Well.
conservation is v star j equals 0.
Yeah, conservation is a. Let me just get the notations straight. So that was the definition before. So I'll switch the names so not to confuse with the previous definition. So that I'll refer to that one as the magnetic, and that one will be the electric, to just conform with the previous definitions. So what is the physical interpretation of those symmetries? So first of all, observation number 1, which is easy, it's an exercise, is that you can verify that the corresponding charges, you can construct some charges out of this. You can construct some charges out of those currents in the way that we've explained before, by integrating them over two surfaces. You can verify that those charges commute with all local gauge invariant operators. And this comes back to a question that Sasha asked, which is how does it act? How those symmetries act? So we'll see it, we'll understand it now. With all local operators. So those symmetries don't act on local operators, nor do they act on particles, because that's the claim to fame of higher symmetries. They act on extended objects. So if you were to, basically your exercise amounts to the following thing. This exercise amounts to proving the following thing: that the way the charge acts on the fundamental gauge field, which is the dynamical gauge field of Maxwell, is that it shifts it. So this is the transformation that this charge implements. It takes a mu. This is the electric one. That's the transformation that the electric charge implements. It takes a mu to a mu plus lambda mu. And what is lambda mu? Lambda mu is a closed one form. But it doesn't have to be a derivative of something. But it does not. But it doesn't have to be d mu of some omega. So lambda mu obeys d nu lambda mu, anti-symmetrized, equals to 0. So that's how the electric symmetry here acts, and it's an exercise for you to show that by just commuting the charge or the current with the gauge field, and you'll see what. So that's a quick way to see that local gauge invariant operators can never be sensitive to such a symmetry, because local gauge invariant operators are constructed out of the field strengths, and since this is closed, this is never going to influence the field strengths.
So
Yeah.
this will be at least locally
Right. Right.
Even if not.
Right. So this does not introduce infinitely bipoint arrest. We'll discuss it soon. I'll say it. I'll say it precisely now. So this is a non-trivial transformation of the gauge field. It's not a gauge transformation. It's not necessarily a gauge transformation, but it does not act on any local operators. However, from this discussion, it's clear that it acts on Wilson lines, electric Wilson lines that are supported on some closed curve. So let gamma be some closed curve, closed non-contractible curve. If we shift the gauge field by a closed one form, lambda mu, the Wilson line will transform just by an integral of this lambda times the original Wilson line. So you see that so it's not a gauge symmetry because closed Wilson lines may transform under that. So under gauge symmetries, closed Wilson lines are by definition invariant. But under such transformations, the closed Wilson lines may transform. And the whole point is that if this was a total derivative, this would be 2 pi, e to the I 2 pi, and that would be 1. But since it doesn't have to be a total derivative, it may be a non-trivial phase. However, since locally you can always write it as a total derivative by Poincaré's lemma, you don't gain infinitely many symmetries out of that. You just get a U1, which is essentially to every closed curve, you get one U1. Yeah?
Where did the algebra require that lambda be closed?
That's just what you get if you solve this equation. I mean, it's an exercise. You have to show that this is a symmetry of the problem. You have to try to act on it just by canonical commutation relations. Compute the canonical commutation relations of this with the elementary gauge field A, and that's what you'll find. It will come out of the computation. Well, an easy way to see that that's a symmetry is that if you did not require that it was closed, that would not be a symmetry. For instance, if you could add something that's not closed, it would mean that you can change the electric field locally. But the electric field is a physical observable. The energy density is a physical thing. You cannot change the energy density. This allows you to change the gauge field while not changing the electric field locally. And it's also not a gauge transformation. Okay? So this is a transformation that's kind of doesn't change anything that's physically observable, like the electric field, locally observable, like the electric field or the magnetic field. But it's not a gauge transformation.
You put that in by hand, right?
By hand, but what do you mean by hand?
That you don't want to change the electric field.
Well, it couldn't have been a symmetry otherwise. That's why it gotta come out of the computation. Something that changes the electric field locally cannot be a symmetry. So this is an object that's neither a gauge transformation, nor does it change any local observable. However, it acts on Wilson lines. So these are the objects that it acts on. It acts on strings, Wilson lines, the objects that are created by, when you take a Wilson line, you act on the Hilbert space, you create a string, or like some flux tube of the electric field that can then evolve in time. And those objects will be charged.
So, Zohar, strictly speaking, the charge should be the integral of this over
A two surface.
a two surface.
Yes, exactly.
So it doesn't just, I mean, this, naively, you could imagine this lambda having support throughout space, but
This lambda is a function of space, it is.
but it's going to be zero almost everywhere if you try to figure out what it is from doing canonical quantization, because the charge, you have to pick the surface that you integrate the charge.
That's right, but also when you study how ordinary symmetries act on local operators, you have to pick a zero form, like the parameter that allows you to do the transformation. Here the parameter is like how these two surfaces oriented, so that's already it's already included. That's an arbitrary function of space, which is a closed one form. Now, it's harder to describe how this one acts on the Hilbert space, or on the elementary variables, because it does not act on the fundamental gauge field A mu. However, if you were to dualize the gauge field to the magnetic gauge field, you would get the same formula. So, in summary, what JE does, it acts on the electric Wilson lines. Okay. The electric Wilson lines have to be properly quantized. Since the gauge group is U1, the electric particles that can propagate are a mass carry integer charge. So there might be a coefficient E, which is an integer. Sorry, it's not the same E. Let's put an N. So N must be an integer. So this is the most general possible Wilson line. It's labeled by some integer. And JE acts on that Wilson line by rephasing it. JM is a little bit harder to explain since it doesn't act on this local variable A mu, it acts on the dual variable. So if you've ever seen T-duality. In 2 dimensions, it's a little similar. There is a symmetry, which does not act on the compact scalar, but it acts on the dual compact scalar. That's in Polchinski's second chapter, probably, in Polchinski's book. So Jm is very, very similar to the dual shift symmetry of the C equals 1 scalar. So Jm acts on the dual gauge field. So it's hard to write an explicit formula in terms of this gauge field. But it's easy to write what Jm does in terms of physical observables. So Jm acts on 't lines. What is a 't line? So a 't line is a world line of a magnetically charged, of a Dirac monopole. So this is the world line of an electric particle of charge n. But you could also discuss the world lines of magnetic monopoles. World lines of magnetic monopoles. And the key thing is that magnetic monopoles must obey the Dirac quantization condition, which in some units is like this, or this is some integer. So this is the Dirac quantization condition for the U1 gauge field. And you can then take a magnetic monopole with some charge G that obeys the quantization condition, where E is the elementary electric charge. And we can call it the 't Hooft loop, which is supported on some curve gamma. And what Jm would do is to rephase that guy. So this rephases the electric world line, and Jm would rephase the magnetic world line. So the U1 times U1 one-form symmetry acts on the 't Hooft lines and the Wilson lines. The 't Hooft lines and the Wilson lines, however, are not arbitrary. They have to obey this mutual quantization condition, that the only allowed 't Hooft lines have to be integer in those units. And the only allowed Wilson lines have to be integer, so integer in the sense that their electric charge must be an integer, because our gauge group is U1. Are there any questions about the U1 times U1 symmetry of Maxwell theory? Yes? Yeah, if you're the best way to think about those symmetries, it's true to say that there is U1 times U1 symmetry in infinite flat space. Because even in infinite flat space, you can still act with Wilson lines on the full space and create like an infinite flux tube, even though it's QED. Okay. However, it's much better to discuss those symmetries when you define your infinite volume theory by a sequence of finite compact manifolds that become ever bigger. And you could take that limit in many ways. And some of those ways could include a non-constructible circle, such as you could take the limit by going over the 4 tori. So it's best to think about it at large finite volume, and then it's manifest that there is such a symmetry. But it's also correct to think about it at infinite volume.
So
yeah.
You could have such a symmetry with no restriction of being in the homology if you take the action to be f tilde rather than x.
Correct. Yes. If your action is topological, you might get a much bigger symmetry. That's correct. Any more questions about Maxwell? Okay, now I want to discuss a little bit how to break those symmetries. Those are symmetries of just the free photon, okay? So how do we break those symmetries? So let's do some a little bit of audience participation. How to break J electric. Does anybody have an idea? How do we modify Maxwell to break J electric? Which modification of Maxwell are you aware of that would lead to destroy the conservation of this J electric equals F? How would we break this conservation equation? No, just students are allowed. Huh? Yes. Very good. This is exactly what we're adding electric charges. So let's do an example. Suppose I added an electric charge 1. What would remain of JE? If there is a propagating electron, what remains of JE out of this U1 symmetry? U1 is broken to what? U1. U1 one form symmetry. Yeah, exactly. So if we added just one electric charge, U1 times U1, electric times magnetic, breaks to U1 magnetic. But if the only dynamical particle was a charge 2 particle, then what would happen then? We would get a Z2 times U1. We could get Z2 electric times U1 magnetic, right? If the only dynamical particle had charge 2. Because then the Wilson line for a single charge so the single charge particle would be a probe particle, and its Wilson line would be a good observable that's not screened, and therefore we'll get a Z2. We would still have got a Z2. How do we break J? How do we break J magnetic? Does anybody have an idea how to break J magnetic? No, just students are allowed. How to break J magnetic, does anybody know? Yeah, we can add massive magnetic monopoles. It seems scary because you don't read about it in Peskin and Schroeder, but it's allowed. You can add a massive magnetic monopole. I mean, even in QED, we don't know if magnetic monopoles exist, right? They're still being searched for, and there might be a very heavy magnetic monopole that QED that is added to the Lagrangian of QED. So you could ask, does the Lagrangian of the standard model have U1 magnetic? We don't know. But the whole premise of the program of looking for magnetic monopoles is that it does not. Well, if you include gravity, then there are strong arguments that there are probably magnetic monopoles in the form of black holes, which carry magnetic charge. But it's a well-posed question even in field theory. Okay? Yeah?
I think there might be some confusion in your notation before you called F versus J magnetic.
So yeah, I wanted to conform with my previous notations. So the J electric is F and J magnetic is star F, because I wanted the conservation equation to be this star of J to conform with the first lecture. And therefore to break, so you see that if you added dynamical charges, this star of F would not be 0. However, this star of star F would still be 0.
Wait, you just switched back. Sorry, is the charge the integral of J or the integral of star J?
Star J.
Okay.
Yeah, the charge is always the integral of star J, because and that's the conservation equation. So to break the conservation of J magnetic, you need to add magnetic monopoles. Dynamical, not probe magnetic monopoles, dynamical magnetic monopoles. Probe magnetic monopoles are those Wilson lines. Okay? Is it okay now?
Why should the monopole be massive?
It could be also massless, yeah. Yeah, in both cases it could be massless. It could also be massless. It doesn't have to be massive. Massive or massless, okay? Any other?
Just made a statement about gravity. I mean, isn't it true that quantum gravity would require the existence of magnetic monopoles because of some instanton effects?
I think it would. I mean, basically, what people believe is true is that in quantum gravity, that there are black holes. You can construct smooth black hole solutions which carry magnetic charge. There are such solutions. There are like variants of the ordinary charged black holes that appear in textbooks. So since such black holes can be constructed, then they seem like smooth solutions to GR, then they might be as well in the Hilbert space, and then the symmetry will be broken because there are dynamical magnetic monopoles in the form of black holes.
So,
Yeah.
your U1, it's important for you that they are compact.
Yeah. So
you have to mention
you can also discuss.
because otherwise.
You can also discuss what happens if.
If you say U1, then it's
No,
You can also discuss what happens if the gauge group was R. Shimon. You could also discuss what happens if the gauge group was R. So what is the answer then?
R. No.
The U1 instead of U1 times U1, what do you get?
R. Oh.
You just get one copy, R, because there are no magnetic monopoles,
Right.
and the electric charge could be anything.
Yeah, but no magnetic.
So there are no. So if your gauge group is R, you just get R. That's the one-form symmetry. Okay, now a much more interesting. Now we're already sort of mentally ready to discuss SUN and to make the central claim about SUN Yang-Mills theory, SUN gauge theory.
Are there any physical consequences to this?
Yeah.
To form symmetries?
Oh yeah, of course.
What are the consequences?
There are many consequences, but I'll discuss. I want to concentrate first on the consequences for non-abelian. You'll see that there is an anomaly, and using that anomaly, we'll be able to make concrete claims about the dynamics of non-abelian gauge theories in 4 dimensions.
What about Maxwell
About Maxwell's theory, it's hard to imagine something that people didn't know in the 19th century.
You can say the existence of the. You can say the photon is a Goldstone boson, right?
Yeah, that's something that I explained in the previous lecture, that you can think about the photon, the familiar photon, as the Goldstone boson of U1 electric times U1 magnetic. So that's something that I already explained the last time. You can do a little bit more. I can mention one additional thing, which is the question of whether you remember that we discussed that higher form symmetries can be spontaneously broken or not. You can ask, what is the fate of U1 electric times U1 magnetic as far as spontaneous breaking is concerned in pure Maxwell? So in pure Maxwell, the Wilson loops for the electric charges obviously do not confine, and likewise the Wilson lines for magnetic monopoles do not confine. So this is actually spontaneously broken in Maxwell. And the Goldstone boson is the electric or the magnetic photon. So in Maxwell, pure Maxwell, this is spontaneously broken. But an interesting question to the students is, let's suppose we do this deformation, where we add a single electric charge, which is a scalar field. So let's add the scalar field phi. This is a homework exercise. We add the scalar field phi of charge 1, electrically charged 1. So then we have U1 magnetic. This symmetry still remains according to this claim. A question for you for the homework is to decide whether the Wilson lines of the monopoles are confined or not. Okay? There are two cases here. One in which the scalar field is heavy with positive mass cord and the gauge symmetry is unhiggsed. And the other case is where the scalar has negative mass cord, higgses the gauge symmetry. And I want you to see what happens to that U1 magnetic symmetry. Is it broken or unbroken? And in fact, it's an interesting order parameter for that phase transition. That's why I'm asking this question. So it turns out, so the model is going to be m squared phi squared plus phi to the 4. And please discuss the fate of this symmetry for positive m squared and negative m squared, and argue that there must be a phase transition, just in ordinary scalar QED. And then you can try to understand if that phase transition is second order or first order. That was found in the 70s, but it would be nice for you to learn that answer. So in the 70s, people have found whether an interesting property of that phase transition, whether it's second order or first order. Okay, this is the homework. So this is another small application that you can recast some phase transitions in the language of symmetry, higher form symmetry breaking. Previously, that phase transition didn't have like a clear order parameter. Okay, so now let's switch to the main topic, which is Yang-Mills theory, pure Yang-Mills theory. And I'm only going to discuss the gauge group SUN. The discussion of other groups is full of various subtleties that are of no concern right now. So this is going to be the Lagrangian. Okay, this is going to be the Lagrangian, the quintessential strongly coupled theory. And the reason that I've spent like an hour discussing that quantum mechanical model is that it's actually extremely analogous to many properties of Yang-Mills theory. The theta parameter in particular has some similar properties. Remember that the theta parameter in that quantum mechanical model was 2pi periodic, and the same is true here. In the quantum mechanical model, so there is an analogy with the quantum mechanical model that this is like Q dot essentially. And this analogy makes sense because integrals of Q dot are integer mod 2pi, because Q can also go around the circle like an integer number of times. Integrals of that object are also integer mod 2pi. This is due to the fact that this is the second Chern class. So this is the main thing that's important to keep in mind, that there is this kind of parallel. Another very important parallel is that I've given you a homework exercise to show that there is a unitary transformation in quantum mechanics, a similarity transformation between the Hamiltonian at theta equals 0 and the Hamiltonian at theta equals 2pi. The same is true in Yang-Mills theory. There is a similarity transformation. If you construct the Yang-Mills Hamiltonian, you can prove as a simple homework exercise that an exponential of the churns of some object that I'll define in a second implements a similarity transformation. So that's the same as h of theta 2 plus. And this is really just completely analogous to, just a second, to that property in quantum mechanics that I've given you as a homework exercise, where so the Chern-Simons action is defined as an integral over space of AdA plus 2/3 A cubed and trace. So this is 1/4 pi. So that's really analogous to that property in quantum mechanics that you've hopefully worked out at home, showing that theta is indeed 2 pi periodic. So that's the formal way to show that theta is 2 pi periodic. There's a good unitary operator in Hilbert space that implements a transformation of theta by 2 pi. So that's a similarity transformation. Okay, so we're going to discuss that theory now, and its symmetries, one-form symmetries, and its infrared dynamics. Are there any questions?
Why do you write the star behind the F?
It's star of the whole thing.
I just wanted I just wanted the Lagrangian to be a scalar. Yeah. I just wanted the Lagrangian to be a scalar object. Just. Yeah, I can. If you want, I can write it with mu indices. No. Okay. So what we need to discuss are the symmetries of this problem, one-form symmetries, and then the key thing is going to be that the quantum mechanical model parallel is teaching us something about anomalies. So the structure of anomalies of this theory will be parallel to that what we found in quantum mechanics, and this will allow far-reaching, interesting conclusions about Yang-Mills theory. So that's what I want to show you now. So let's discuss the symmetries of this model. First of all, as in the quantum mechanical model, the question here is what is the analog of the SO2 in the quantum mechanical model? So remember in the quantum mechanical model there was like Q going to Q plus alpha. What is the analog in Yang-Mills theory for that SO2? And the analog is a one-form symmetry. So we need to understand the one-form symmetries of Yang-Mills theory. Remember that in QED, the one-form symmetry was U1 times U1. In pure Maxwell, not in QED, I'm sorry. In pure Maxwell, it was U1 times U1. This is pure glue. So we need to understand what is the one-form symmetry of pure glue. So yeah, one-form symmetries are always abelian. Yes. SO2 is abelian. SO2 is just U1. I'm not claiming that the one-form symmetry of pure glue is SO2. I'm just asking, what is the analog of the shift symmetry on the ring in Yang-Mills theory? I'm just going to use, you see, instead of proving that Yang-Mills theory has certain anomalies, I'm going to make a parallel between that and quantum mechanics, and hopefully you'll believe that this is true. Okay? That's the idea. I'm not going to prove it mathematically. Okay, so what is the one-form symmetry of pure glue? That's the interesting question here. So there is no, you cannot write this thing F mu nu, you cannot write this or that, because these are not gauge invariant. But this only proves, yes, we cannot write either of these things because they are not gauge invariant, but that doesn't mean that there is no one-form symmetry. It could be discrete. That just means that there is no local conserved current, so it's not continuous. But it could be a discrete symmetry. There could be an interesting discrete symmetry, which is a subgroup of that U1 times U1, so to speak. So the intuitive way to understand the answer, at least the first step in understanding what's the answer, is to observe that you can think about Yang-Mills theory as like it's basically like a free photon, except that there are many photons, and they can interact with each other. And in particular, the photons are in the adjoint representation of the gauge symmetry. So you can think about the gluons. The gluons are in the adjoint of the gauge symmetry. And here we can use, therefore, the analogy with free Maxwell that had a propagating charge 2 particle. So if we only had a propagating charge 2 particle, what would have been the one-form symmetry? It would have been Z2, as we just discussed. Here, there are propagating particles in some representation of the gauge symmetry, but there are no propagating particles in pure glue in the fundamental representation, for instance. There are also no particles in the symmetric representation, all the way up to the adjoint. So this is the electric one-form symmetry. You get a Zn. The Zn comes from the fact that if you put a Wilson line in the fundamental representation, it will have a very complicated back reaction on the gauge fields, but you could still measure at infinity the charge that's inside in space, modulo n. You can emit gluons, but gluons cannot completely screen a fundamental line because gluons are in the adjoint. They have, if you are familiar with Young tableaus, gluons have n boxes, while the fundamental representation has only one box. So what you can measure at infinity, even though the equations are nonlinear and complicated, and there can be quantum fluctuations, you can still measure the number of boxes, mod n. So that's where this Zn comes from. So this is the number of boxes in the Young diagram, mod n. That's where this Zn comes from. Okay. An equivalent way to think about it is that refer back to Maxwell theory with a charge 2 particle. So in Maxwell's theory with a charge 2 particle, there was a gauge transformation that did not act on any of the dynamical fields, which is a gauge transformation by 180 degrees. Here, there is a gauge transformation that does not act on the gluons, which is in the center of this SUN gauge group. So if you look at gauge transformations that are proportional to the scalar matrix, so it's 2 pi I k over n times the unit matrix, those gauge transformations do not act on any of the gluons because the gluons are in the adjoint representation, and that cancels out. So this k is associated to the elements of Zn. That's another crude way to understand where this Zn comes from. But this is not a gauge symmetry. This is a gauge symmetry. This is not. This is an actual symmetry. So this presentation is very confusing. It's best not to. I mean, it's best to think about it only as a qualitative analogy. The Zn is a physical symmetry. In fact, this physical symmetry acts on objects that we're familiar with. It acts on the objects that are created by acting with a Wilson line at some fixed time on the Hilbert space. We get flux tubes. Those flux tubes have been seen in the lattice. They're the reason that Yang-Mills confines. And these flux tubes are protected by the Zn symmetry. So if on the lattice you can create such a flux tube, it will never decay. So this Zn acts on flux tubes. Okay. Now what about the magnetic symmetry? Yeah.
What's at the end of the flux tube?
It's infinite. I imagine a flux tube which has periodic boundary conditions. So there are physical objects that carry this symmetry, which are extended. Those are not point particles. They are not globules. They are extended objects. Now, what about the magnetic one-form symmetry? This is harder. What about the magnetic? Is there a magnetic one-form symmetry? This is a little bit harder to understand, and I'll give you a qualitative argument that there isn't. There is none. And the argument goes as follows. So there is I'm giving you a qualitative argument. It's not a proof, but the answer is correct. So we have a Zn electric one-form symmetry. And in fact, I could have modified this model a little bit. So while not destroying this Zn electric one-form symmetry, I could have added, for instance, adjoint scalars. I could have added scalars phi in the adjoint. I could have done that without destroying the Zn electric one-form symmetry. And in fact, it doesn't destroy it wouldn't have destroyed the magnetic symmetry either if there was one. But let's do that for a second. Let's add some massive scalars phi in the adjoint. In that case, there is a construction by I think Tuft, Polyakov, and others of a magnetic monopole. So the system already admits finite mass dynamical magnetic monopoles, unlike QED. This is not true in QED. In QED, or just scalar QED, I mean, if you took the free photon and you added the massive scalar, there would not be magnetic monopoles which are of finite mass and dynamical. There would only be probe magnetic monopoles. But in non-abelian theories, Tuft and Polyakov have shown that adding dynamical scalar fields in the same representation that anyway already exists leads to finite mass dynamical magnetic monopoles. So therefore, the system cannot inherently admit a magnetic symmetry.
Can't you just say SUN is simply connected? So,
Well, that would be.
so there's nothing for them to act. There's nothing for a magnetic one-form symmetry.
Well, that would be.
There's no tough lines, right?
Yeah, I mean there are general arguments. I'm just
There's no
giving.
one to ask for. I mean, there's no candidate thing for the symmetry to act on.
Yes, but I want to refrain from making
Break the signal.
mathematical arguments.
You need the potential.
This is. Yeah. So this. So therefore, there are dynamical.
Then there would be. Then there would be. Yeah, if it's SUN mod Z,
Uh,
that's totally different. But,
So there are dynamical monopoles, which in fact carry the unit possible magnetic charge. So they obey Eg equals n for the U1 Cartan subgroups, n over 2. And so there is no sense of having protected world lines for magnetic monopoles since they already exist as dynamical particles. And of course, there are general criteria that you could devise following GNO essentially for the existence or non-existence of some dynamical monopoles. But for SUN, this is the answer. So there is no magnetic symmetry. However, there is a ZN electric symmetry. And that is the analog of SO2. So it's correct to think about the one-form symmetry as the analog of SO2. It's like a subgroup of SO2. You could think about it in that way. It's a good analogy to think about the ZN one-form symmetry as analogous to the SO2 in the particle on a ring model. Next, there is another important symmetry in the problem. Are there any questions about this analogy? Yes?
So there's nothing like this analog of T-duality as you explained in QED?
Yeah, in pure Yang-Mills theory, there is no one-form symmetry that's magnetic. There is only an electric one-form symmetry. However, there is a generalization of T-duality nonetheless. I can say, just for the more advanced students, you could study SUN gauge theory, pure SUN gauge theory, that has a ZN one-form symmetry, which is electric. Another model that you could study is a PSUN gauge theory, which has a one-form symmetry, which is purely magnetic, but there is no electric one-form symmetry in that theory. And in fact, there is a duality between them that's analogous to T-duality, where the magnetic symmetry and the electric symmetry get exchanged. And that's in QED, in free Maxwell, it's a self-duality. So you have U1 times U1, and the U1 and the U1 get interchanged, like in T-duality in 2 dimensions. But in non-abelian gauge theories, there is an analog. It works a little bit differently. It takes one gauge theory to another gauge theory, and the electric and the magnetic one-form symmetries get exchanged. This is called S-duality in the literature.
you need supersymmetry.
There are examples like Seiberg-Witten theory and n equals 4, where this can be made concretely correct. I mean, as a duality. Yeah. Now I want to mention the last symmetry, and then.
One thing, that's the analog of this hoop line in Yang-Mills theory.
So here there are Wilson lines, which create flux tubes, and here there are 't Hooft lines, which create dual flux tubes. Sorry, this is Wilson, and they get interchanged under this S duality. So that's the best analog of the T duality for non-abelian gauge theories. Okay, now the last symmetry that I want to mention is the time reversal symmetry. And that is going to be the analog in quantum mechanics. That's going to be the analog of C. You remember C from the quantum mechanical construction, which flipped the sign of Q? So that's going to be analogous mathematically to time reversal symmetry in Yang-Mills theory. Similarly to the fact that there was a charge conjugation symmetry in quantum mechanics only at theta equals 0 and pi, time reversal symmetry is a symmetry of the strong interactions only at theta equals 0 and pi. Indeed, this term that I wrote I theta over 8 pi squared star f wedge f, this term is not invariant under time reversal symmetry unless theta and minus theta are the same mod 2 pi. And theta can be the same mod 2 pi only if theta is either 0 or pi. It's the same as in the quantum mechanics model, which we discussed in great detail. So time reversal symmetry takes that to minus that, and that's it. So we see that we have an interesting conjecture now based on this analogy that perhaps there is an anomaly, like in quantum mechanics, that involves time reversal symmetry and the one-form symmetry.
Isn't it better to think of this as CP?
Yeah, because of the CPT theorem, CP and T is the same thing, because CPT is always an unbreakable symmetry in relativistic quantum field theories. So you can think about it as either CP or T. It's the same. It's the particle-antiparticle symmetry or the time reversal symmetry. Same thing. So the main claim is going to be that pure Yang-Mills theory has a mixed anomaly between time reversal symmetry and Zn. Now, in the quantum mechanical model, the interesting thing about it is that in the quantum mechanical model, we had the free limit, where we could have demonstrated that there is such an anomaly by computing the partition function. It was not under doubt that there is such an anomaly. Here, you cannot do it. You cannot compute the partition function. And so you have to resort to more fancy computations, which I'm not going to review, but I'm going to take it for granted that there is such an anomaly. And we're going to infer some consequences for the finite temperature phase diagram of Yang-Mills theory and the zero temperature phase diagram of Yang-Mills theory just from the existence of an anomaly between time reversal symmetry and Zn one-form symmetry. So there is a mixed anomaly. And in the next lecture, we're going to draw the phase diagram of Yang-Mills theory at finite and zero temperature. As far as this, we're going to draw the phase diagram, and we'll see what are the constraints that are imposed on the phase diagram due to that anomaly. And you'll see that these are highly non-trivial constraints. And later, we'll discuss Chern-Simons theory and show what are the consequences of this anomaly for domain walls. And this is going to be the content of the next two lectures, essentially. Yep. Yeah, there are some fine prints all over the place. I'm trying to avoid these complications. Yeah. Any other questions?
If there are no other questions, let's thank Zohar. צריך כמובן לשבור את החבורה.
כן,
דבר אחר, בזמנו, in the old days, בנינו, זה מילים של טוטה, שאתה לוקח n כאלה, והג'אנקשן מתנהג כמו מונופול. הג'אנקשן של n, zn פלקסס, זה בעצם המונופול. שאם היית, אתה יודע, זה בבאסה גבוהה.
כן, זה גם נכון, אתה יכול לעשות את הארגומנט הזה גם.
לא, השאלה אם אתה יכול יותר יפה להראות את זה. אבל in the old days, הג'אנקשן של n כאלה, זה היה הדבר שהיה אמור לעשות קונדנסציה ולתת לך את הקונפיינמנט. הקונפיינמנט זה לא העובדה שיש לך את אלה, זה הקונדנסציה של המונופולים, שזה n כאלה. ואם אתה יכול לעשות את זה עכשיו לאור כל ההבנה, משהו יותר, להגיד את זה בצורה טובה יותר, זה היו מילים, in the old days זה מילים. אבל זה היה הרעיון. עכשיו כמובן אם אתה לוקח על הלטיס ZN גייץ' תיאוריסט, אז אתה יכול להראות שאין כאלה, יש לך ג'אנקשן כזה ודברים. השאלה אם אתה יכול...
לא חשבתי על זה.
אז תחשוב, כי זה אחד